Hello and welcome to Unit 3, Brief Calculus. I'm going to try to do a video this time before we get into any of the work in the unit, and I'll also make one with the practice test going over the solutions. And just want to introduce this one this time. This will be a short video on two topics. There are three major ones in this unit. The first one is concavity, and the second one is optimization, and the third is related rates. And concavity you may have heard of in your algebra class, and we're going to address it rather lightly. Extrema and optimization we will do a little more in depth because it's a great technique to do some relevant real-life problems, and likewise with related rates. So tonight we're going to talk about concavity, and the basic idea about concavity for here and now is that the shape of the line, the curve, the function is labeled, and your book points out that if it looks like a U or a cup, it's concave up, and if it looks like a frown or an upside down U, it's concave down. And maybe you're thinking, well, it's pretty silly just to label things that way, but inherent in that are some things about slope, which we will talk about briefly, not as in depth as we used to have to go into in previous courses because, well, you'll see why. So let me grab a marker. So concavity, just like your book says, concave up and concave down. And again, the reason for addressing it is not just to describe parts of a curve. For example, a function that does this has an area that's concave down, concave up, concave down again. And by the way, the book also mentions that when it changes concavity, it does so at a point of inflection. So some vocabulary, but the big question is, why do we care? And we care because of the reference made to slope. Here we see that the slope, though pretty steep and positive, is leveling off, and we're getting to the top or the maximum part of the curve, and then we're going to start going downhill again. So we're having a slope that's really decreasing. It started off pretty steep, but then it leveled off, got to zero, and now it's negative, or we could say decreasing even more because of the minus sign in front. Its slope is steep but in a negative direction. Then it gets to that point of inflection and concavity changes. It's now concave up on this interval. And again, why do we care? Because the shape says we're picking up steam. We had a slope that started off steep, leveled off, descended, got more and more negatively steeper, leveled off down here to a zero, a minimum value, and then began to pick up steam again. So we went from negative to zero, which is getting larger, and then we went from zero to small positive values getting steeper. And then the replay of the first segment will happen here again. You've heard of expressions like the unemployment rate is decreasing at an increasing rate. Well, that talks about a particular shape of concavity. Decreasing, but at an increasing rate. And where do you think that might be on this curve? Getting more negative, getting steeper in a negative direction. Think about where that picture would be. And other instances of concavity in the news as far as increasing, decreasing rates, and the rate at which those rates change. So inherent in this language is change of rate of change of rate. So we're talking about a derivative of a derivative. A derivative watches the behavior of a function, and the second derivative watches the behavior of the first. So if this function is f of x, and we're talking about concavity, we're talking about things that talk about the derivative of the function. So we're talking about derivative of the derivative. We're going to watch behavior exhibited by the derivative of the function. So we call that the second derivative. And most likely we'll use this notation. Every once in a while you'll see this notation. So we want to write it like this. And the reason the 2 goes here is that sometimes we take out that y and we put in what y is equal to right there. But if we're writing shorthand, sometimes we just write the y. So the 2, meaning second derivative, goes there. And down there, there's never any rearrangement, so we just put it on the outside. So a whole lot said and a little bit bored. We care about shape because it tells us the behavior of the function. And to watch the behavior of the function, we need another derivative to watch the first derivative. Because when we say that the concavity is up, we're looking at this segment of the graph, and we know that we hit bottom here. So that's something we know the shape's going to portray to us. When it's down, we know that there might be potential maximums to the function right there, because horizontal tangent line, you got to the top and then you're going to go back down again. So we bring into play, notice that this behavior is linked with tags on the second derivative. So this second derivative, concave up, is going to be positive. This concave down, the second derivative, is going to be negative. And let's take an example and show you what that looks like. So simple function, f of x equals x squared. Its first derivative is 2x, and its second derivative is just taking a derivative again, is going to be 2. Well, we know that 2 is 2. It's always 2, it's always positive. So let's check that out with the graph of y equals x squared. It looks like a parabola, a little better than my parabola, but a shape like this that is always concave up. This is always positive, second derivative positive, concave up. If we had a function such as the flip of this parabola, looking like that, we're probably anticipating concave down. A quick check of derivatives, using the power rule, and using the power rule one more time gives us a -2. For any x, it doesn't matter, there's no place to put an x, so it's always -2, indicating it's concave down. Second derivative negative, concave down. And probably shouldn't get so lazy. I'll probably write negative like this, and positive like this. I'll try to remember. Let's go to the next topic.